Recording started.
Hello, my name is Jonathan Hill, and I'm one of the mission planners here at Arizona State University's Mars Spaceflight Facility, which means that I'm one of the scientists who actually gets to operate the cameras that we've sent to Mars. So I spend about half my time sending commands and taking pictures with the Themis camera, and the other half of my time I operate the two mini-test instruments aboard the Mars rover's Spirit and Opportunity. But today I'd like to talk to you about some of the global maps that we have available, either through JMARS or through our websites, that might be helpful for you as you work on your MSIP projects. So the first map I want to introduce is the MOLA map, and this is probably the one that you've worked with already, and is probably the easiest one to use. MOLA stands for the Mars Orbital Laser Altimeter. So basically, this was an instrument that flew to Mars in 1996 on the Mars Global Surveyor satellite. And when it was operating around Mars, it would just send down millions and millions of little laser pulses and would measure how long it took those pulses to bounce back to the satellite. And from that, we were able to measure the height of every part of Mars. And so we turned it into a map and have color-coded it here based on the elevations. So if you're working on MSIP, what exactly can you use this map for? Well, the main use is for context. So if you're looking at a Themis Vis image or a Themis IR image, it may be difficult to figure out what you're looking at because you're looking at such a small portion of Mars. And sometimes it helps to zoom out and get a better idea of the big picture, what's around it. And so this map can be useful for that. We can also use this map to determine qualitatively what elevations we're looking at. So in this map, warmer colors, things like red, orange, and even white, those are really high elevations, the highest points on Mars. The cooler colors, the light blues, dark blues, purples, those are lower elevations. So it gives you a sense of the topography on Mars and the general elevations of the areas that you might be studying. The next map I want to talk about is the Themis DAIR Global Mosaic. So this is a map that we compiled using Themis DAIR images. We took about 25,000 of our images and blended them all together into a nearly seamless map of the entire planet. And that makes this the highest resolution global map that we've ever made of Mars. Now, as you can see up near the North Pole, there are a couple large gaps just because during most of the year there's a lot of clouds up there, and so it gets difficult to take IR. But pretty much anywhere else you want to look on the planet, you're going to find coverage in this map. All of these smaller gaps look artificially big in this version of the map. When you actually zoom in, they're very, very small. So what can you use the DAIR Global Mosaic for? So this map is really useful for measuring features, especially those that are too large to fit in a single Themis Vis image or a single Themis IR image. So things like the lengths of channels, even the length of some wind streaks, the diameter of volcanoes, really large features. This map is also really helpful for crater counting. So if you're interested in trying to determine the relative age of two different areas, you can count the number of craters they have. And the older a surface, the longer it's been there, the more craters it's acquired over time. And so you can work out relative ages that way. And since this map covers a lot of area at really high resolution, it makes it easier to count those craters and build up those statistics. Now, a related map is our Themis Night IR Global Mosaic. So this is also a map created using Themis IR images, about 18,000 of them, but these were images taken specifically at night. And so instead of looking at the temperature of the surface during the day, we're actually watching to see what the temperature of the surface is after the sun goes down and things begin to cool off. So how would this map possibly be useful for your projects? Well, this is a really good map for finding wind streaks, whether they're erosional or depositional. Erosional wind streaks, which form when there's an obstacle like a crater or a mountain, and as the wind flows around it, it scours away the dust behind that obstacle. So those features usually appear bright white because you're taking away really fine dust and exposing bedrock. And bedrock is really dense and holds onto its heat at night. So in these images it appears really bright white. Depositional wind streaks are exactly the opposite. In those cases, the wind is depositing sand and other really fine materials like dust behind the obstacle that they're going around. In that case, this map is going to show them as really dark streaks because those really fine materials, sand and dust, will cool off very quickly as soon as the sun goes down and be very cold when Themis flies over and looks at them. So using this map, not only can you find the wind streaks, but you can determine what type they are just by their color. Similarly, you can use this map for any other region to try to figure out what the surface is like. Again, any sandy or dusty areas are going to appear darker, and bedrock or more dense rock fields are going to appear whiter in this map. So not only can you get an idea of what surface morphology features you're looking at, but you can see what they would be like if you were down on the surface. The only sort of caution on this map is it only extends from 60 north to 60 south. And that's because just like here on Earth, on Mars at the poles, during the summer the sun never sets, so we never get night. We can never take night IR images. During the winter, the sun never rises, so we never get the chance to heat the rocks up and then watch them as they cool down. And so we've taken out all the bad data and restricted it just from 60 north to 60 south. The next set of maps are just a subset of all the mineral maps that we have available through JMARS on our websites. These mineral maps were all made using data from our TESS instrument, which stands for the Thermal Emission Spectrometer. And basically this instrument would look down at Mars, take pictures with 152 different infrared colors. So instead of the day IR map or the night IR map that looked at Mars with only one color in the IR, TESS is looking at 152 different colors. And from that, we're able to tell what the rocks are made out of, even though we haven't gone down to the surface and actually examined them. So this map is a really helpful one. This is the surface dust abundance map, basically telling you how much dust is on the surface. So what can you use this map for? The main use is for finding wind features like dust devil tracks or wind streaks. Since those features tend to form in dust, you'd want to go and look for them in areas that have high dust abundances in this map. So like similar maps before, like the MOLA map, warmer colors mean more of something. So in this case, more dust. Cooler colors represent less dust. And if you notice up near the poles, we have areas where it's gray, where there is no color data. Those are areas where, for some reason, we weren't able to see the surface and measure its composition. In this case, the poles are usually covered in thick layers of either water ice or CO2 ice, and since TESS could only look at about the first millimeter of the surface, we couldn't see down to the rock and soil. And so instead of putting in bad data, we just left that area blank. One of the other really helpful mineral maps is basalt abundance. Basalt is what you typically think of as lava rocks, or the type of rocks you would find in Hawaii. It's a really dark color, very black, and gives you a sense of how volcanically active an area has been. In general, Mars is a pretty basaltic planet, just like Earth is a water planet. So you're going to see lots of basalt all around Mars. But areas that have high concentrations of it have probably been volcanically active more recently than other areas. So if you want to study volcanoes, their sizes, the diameters of their caldera, their elevations, anything like that, this would be a good map to help you locate and find some of the smaller volcanoes. Using this map to find large volcanoes is going to be difficult, though. Unfortunately, a lot of those really big volcanoes on Mars because they're so big, they extend really high up into the atmosphere. And when we have these big global dust storms that we see every 4 or 6 years, they will move dust to the top of those mountains, but then once they stop, the winds up there don't have enough power to move the dust around anymore. So it's sort of like a dust trap. And over billions of years, we've built up huge layers of dust in those areas. And again, since tests could only look at about the first millimeter of the surface, sometimes we couldn't see through the dust to the surface. So in this case, any areas like this area around Olympus Mons and the Tharsis volcanoes, there was so much dust, tests couldn't see through to the ground. And so instead of putting bad data there, we just left it out. Now the next map is a little harder to use. You have to make sure you're thinking about it correctly. But a lot of our MSIP groups have used this to do really interesting things, so we wanted to introduce it to you. This is the HEND map. The HEND is an instrument on the Mars Odyssey spacecraft alongside Themis, and it stands for the High Energy Neutron Detector. Basically, when you're out in space, there are a lot of neutrons just flying through space randomly, and when they hit a planet's surface, they do one of two things. They're either absorbed by the planet and stay there, or they get reflected back. Now luckily for us, one of the best things to absorb neutrons is water ice. And so when these neutrons hit Mars, areas that have lots of water ice, they get absorbed. Other areas that are really dry and rocky, the neutrons get bounced back and measured by the satellite. So this map can be used to really determine where is the subsurface ice on Mars. Now the reason it's difficult to use is that the color scheme is backwards, because we're not measuring how much water ice there is. The map is measuring how many neutron reflections we're seeing. So areas that are red are indicating lots of reflections, which means that there's very little water ice in the subsurface. Areas that are cooler in color, those represent fewer reflections of neutrons, which means there's more water in the subsurface. And we know this map is pretty accurate because in 2007, when NASA sent the Mars Phoenix lander to Mars, we landed right about here, up in this big blue patch in the northern hemisphere. And from this map, we were expecting the water ice to be just a couple centimeters below the surface. So Phoenix landed, took out her little shovel, dug down about 3 centimeters, and ran into a huge block of water ice that we weren't able to dig into any further. And so we were able to ground truth this map, and so we know now that it's pretty reliable. Now the last map I want to introduce to you is our geologic map of Mars. So unlike the other maps that actually show you what's on the surface, this map is sort of a graphical representation with different colors representing different geologic regions on the planet. Now unfortunately, this map doesn't really have a key to it, because this was compiled using data from the Viking missions back in the 1970s, and it took almost 2 decades for geologists to go through and actually identify where the boundaries are between all these geologic units. And so their goal was not to determine what the units are made out of, but simply what areas are different from others. And we wanted to show you this map, first of all, because it can help you in identifying regions. A lot of MSIP groups want to do things like study what's the average crater diameter in this region versus the average crater diameter in that region. And because we don't have borders on Mars, this map is the best way to determine where the boundaries are between the 2 different or 3 different regions that you choose to study. Also, a lot of really interesting projects have come out of the students trying to figure out what those units are actually made out of. From the test mineral maps, you can figure out what kind of minerals we see there. From the Themis IR maps, you can tell what the surface is like. Is it rocky, sandy, or somewhere in between? And from the MOLA map, you can tell the elevation changes. Is it a bumpy surface? Is it a smooth surface? So using this map in conjunction with the other maps can teach you a lot about the surface. And that's what we're hoping you're able to do with all these maps, is to meld them together, use multiple maps at the same time to get really interesting information about the region that you're studying. Now, this is just a small subset of all the maps that we have in JMARS and on our websites, but these are the most commonly used, so that's why we're introducing them here. As you're working on your project, if you think it might be helpful to use a different type of map, please feel free to contact us here at ASU's Mars Education Program, and we'll try to point you toward the best maps that we didn't cover today that would be helpful for your project. So we look forward to seeing what you guys can do with these maps, and wish you good luck on your projects.